Akash Dople. I do product management for Extreme Networks for service providers and data centers. And I would like to congratulate Nick on passing 8 terabits. That's a pretty major milestone across the world, so I decided to do something or visualize what that 8 terabytes look like. So if you put Brazil on top of Europe, right, it's a pretty big country. 8 terabits that's why you need 8 terabits. It's going to grow more. From a geographical perspective, it goes from London to Moscow, east-west, Stockholm to Athens, north-south. And if you go even further, you might even include Reykjavik in it. So it's a pretty big country. And when we talk about regional service providers, regional service providers are equivalent to some of the state networks, country networks back in Europe. So each of the states almost covers the size of each country back in Europe. So regional providers are pretty significant when it comes to the geographical spread of the network. So if you take a quick look at the submarine cable maps which come in, they pretty much land at certain sites in Brazil, and then the IXPs take that particular connection and give it to the regional service provider. So if you take a quick look at a sample regional service provider, they usually run according to the fiber runs across the country, and they are made of multiple rings. So I decided maybe I should put this context in and give you a couple of choices as network operators. You can have, based on your pricing, you can have G.8032 as one of the choices. You can have MPLS as one of the choices. You can also look at VxLAN as one of the choices. This presentation is primarily to help you guide and not recommend any one of the technologies. So it's up to you how to choose one of these technologies. So take a look at what happens at the internet when it comes into the IXPs. They essentially go out into the fiber runs, and all these fiber runs either go into business VPNs, mobile backhaul. They also go into mobile packet cores for tier 1 mobile packet providers. You have EPC cores, and you also have a bunch of ISPs, but essentially they are distributed across also through residential triple play networks. There are primarily 3 use cases which regional service providers or regional metro networks try to solve. The first is the residential triple play, which all includes ITT, IPTV, OTT. There's also mobile backhaul, which the presenter earlier mentioned. So there is a front haul, there is a backhaul, and in many cases, depending on which part of the globe you talk to, there's also something known as wholesale backhaul. So a wholesale backhauler is somebody who sits between the cell and the data center for a tier 1 provider and subcontracts the data through their network. So there are essentially 2 mobile backhaul services. They do wholesaling for tier 1 providers. There are about 190 plus wholesale backhaul providers who partner with tier 1 providers. And in addition to that, you also have enterprise services such as internet, university, distance learning, etc., which goes towards the enterprise. Now let's take a look at what happens in a specific IPTV network. Usually there are multiple rings, there is a head end. Most of the cost on an IPTV network or triple play network is in the head end. So that head end, people usually tend to share that head end. And if you look at TV services, if you look at standard TV services, about 250 channels, a mix of standard versus high definition, that's about 2.9 gigs on 250 channels. If you take into account a 4K channel, that all depends on how many frames per second you use, whether it's 24 frames per second, whether it's 60 frames per second, or whether it's a 60 frames per second uncompressed. So usually they do compressed. Nobody tries to do uncompressed. But if you take a look, it essentially is in gigabits, either a 6 gigabit, 9, or 14, depending on what that 4K channel looks like. The most preferred method of an IPTV provider, residential triple play provider, is to do an IP overlay. It's a standard simple IP overlay. Here, the idea is to generally reduce the channel surf time and the channel zap time. to less than 15 milliseconds. So no matter what technology you use, you want to reduce that channel surf and zap time. Let's take a look at what happens if you put an VxLAN on it. Essentially, if you put a VxLAN overlay on it, the rendezvous point has to move closer to the head end. You'll probably need VTEPs with all the IP addresses on the far end, and all the joins have to go all the way to the rendezvous point. Now, the reason I'm mentioning this is because if you do VxLAN multicast control plane, the idea to reduce channel surf time and channel zap time is to take the data stream, the multicast data stream, all the way to the edge. If you take it all the way to the edge through PIM dense mode, for example, then when you surf the channel or when you change the channel through electronic program guides, the time difference between changing the channels is pretty low. So be careful of how you deploy multicast in a VxLAN network for residential triple play. Essentially, no matter what you choose, you have to look at quality of experience. QoE in a residential triple play network, that is dependent on two different things. PSNR, which is peak signal to noise ratio. The second one is MOS, or mean opinion score, and that is determined by human components. Essentially, if you look at peak signal to noise ratio, is determined by jitter and packet loss. What I would say is, in both cases, the audio should not follow the video by more than 15 milliseconds. That way the video gets out of sync. You will also get calls on an IPTV network. This you can measure by a test equipment. Usually speaking, the jitter and the packet loss may not be detected by human perception. What does human perception do is what we call mean opinion scores. Human perception is generally at 16 frames per second. So if you look at 4K videos, they are generally more than 16. They are 24, they are 30, sometimes 40 frames per second. So MOS is not going to affect 4K video. However, if you look at the packet loss at 0.1% or 0.2% or 3%, it's distinctly noticeable even for the MOS scores. So going back to quality of experience, even on a VxLAN network, you have to remember that the jitters on a PSNR should be less than 50 milliseconds, and acceptable MOS should be less than 25. So that's typically what you should design your network to. And then packet loss should not exceed 0.5% if you have more than 250 channels on your triple play services. So moving on, now you have to also overlay your mobile backhaul services, whether it's a front haul, whether it's a backhaul, or whether it's a wholesale backhaul. Any of these mobile backhaul services, they pretty much rely on load balancing techniques. These load balancing techniques can be controlled or dynamic. Essentially, what they need is a good entropy inside that data channel. And that entropy can reside either in a VLAN, can reside in a PW control word, in an MPLS label. It can reside in a source and destination IP, or the TCP destination ports or UDP ports. So the entropy varies based on who's looking at what data path. And then you also need options on nesting that entropy, on nesting that load balancing algorithm. Now, what do we mean by nesting is, let's take a look at a standard layer 2 or G.8032 mechanism. You always have number of links in a port channels. For example, if the port channel is each 100 gigabits, then you have about 6.4 tera, which you can bundle in a single port channel. If you look at MPLS, you can nest it with a higher layer, which is LSP load balancing, which means that I can use up to 32 LSPs to load balance that traffic, and each of the LSPs can be now nested on a 64 100 gig port channel, roughly giving 204 tera in a single channel. And if you look at VxLAN, essentially you do IP ECMP next hops, and then you can overlay that ECMP next hop load balancing. Each next hop can be overlapped with lag or port channel. So essentially, that also gives you 204 tera in a single pipe. Let's look at another example. So when you look at regional providers, you also want to protect your ring. Not only do you want to not only do you want to scale the network, but you also want to protect the ring. So what ring protection mechanisms do you have? Essentially, in a layer 2 ring protocol, half of the ring is always blocked. That's because it's nature of the layer 2, nature of G.8032. In an MPLS, it's an IP MPLS ring. You can actually load balance pretty significantly and evenly across an IP ring. Similarly, across a VxLAN, you can also load balance across an IP ring. In MPLS, you do have a choice to truly provide transparent VLL service if you so desire. Essentially, you're looking at a VLL circuit able to transport control packets for a customer from one point to another without dropping them. VxLAN services may or may not be able to distinguish control packets in a way VLL tunnel circuits allows you to transparently take it out. Protection mechanisms in layer 2 or G.8032 circuit depend on where the failure happens. It can happen either at the ingress, which is closer to the source. It can happen on egress, which is closer to the exit point, or it can happen at transit. The worst case scenario is when it happens in transit, because when it happens in transit, everybody else has to detect where the failure has occurred and have to age certain addresses and relearn them at the same time. There is no faster way to relearn everything in a G.8032 type of scenario. Especially if you're looking at SLAs with 50 millisecond failovers, then it may create issues when it compared to G.8032 circuits. If you look at an MPLS mechanism on ring-based systems, there are essentially 3 options you have. You can do hot standby secondaries, you can do detour LSPs, or you can do bypass LSPs. If you look at hot standby secondary, the secondary path is always up. It's always signaled but never used. Essentially what it means is when the traffic is running on the primary path, if the failure happens, the secondary path is already programmed and up. And when the failure happens on the primary, the traffic switches on the secondary right away as if it was doing an LACP or a port channel failover. So you can actually achieve 50 millisecond failovers for your backhaul networks. If you look at detour LSPs, this is slightly tricky because your PLR, or point of local repair, where the failure happens, you have to have a detour LSP and also sometimes a secondary LSP on standby. So when a failure happens, it goes on detour LSP, and then if secondary LSP is there after some time, the packet will go on the secondary LSP. In terms of bypass LSP, if you look at bypass LSPs, it protects multiple LSPs at the same time. If a failure happens on a common path of the LSP, a standard bypass LSP will actually take all the LSP traffic and will help them recover on the ring. So essentially these are the, in summary, you have 3 options on a ring when it comes to MPLS. Let's look at a VxLAN. What will VxLAN do? A VxLAN, essentially, you will need a faster mechanism to detect failures across your endpoints. Essentially, you'll need a BFD type mechanism to run across your VTEP endpoints. And then currently, the VxLAN for BFD is in draft mode. It's already mentioned over there. But essentially, the IP tunnel failover is based on how fast you can detect failures in your transport IP. Now, if you look at how the BFD will operate in VxLAN, the IP transport on the outer, the VxLAN tunnel on the inner header, the BFD has to run inside the inner header itself, based on VTP to VTP IP addresses. So it lays pretty embedded inside, and depending on how many VxLAN tunnels you have to scale that many BFD sessions. So the chances are that the BFD sessions, if you run in aggressive mode, which is 10 milliseconds or less, it will consume a lot of CPU on a given device. For example, if you have 100 services, and if you want to run all 50 of them in an aggressive timer mode, then the CPU will be utilized in a proper way for those 50 services. So let's take a look at what a metro provider would expect from a VxLAN type network. So if you look at a metro provider, they usually mandate MEF 9, MEF 14, MEF 21. Certifications, sometimes CE 2.0 certifications. So they essentially what they are is how to signal, protect, and failover in a standard way. So if you were to implement VxLAN on an IP ring, you will also need a mechanism to do transport VLANs, meaning you have a service provider VLAN which will bundle all your inner VLANs from the customer and transport it across. You will also need local VLANs to communicate with each other on a VTEP endpoint. In the MPLS world, it's called local VLLs or local VLL forwarding. You will need a customer to talk to another customer in the on the same port. Then you will also need local switching or local VLL type capabilities. You will also need something known as VLAN bundling. For those who don't know VLAN bundling, it's essentially a MAC VRF. And you can do multiple VLANs bundled into a specific VRF, and then the VRF isolates a set of MAC addresses. This is really good if you want to do communications with a layer 3 cloud provider at the other side. So essentially, VLAN bundling is one of the things you'll have to do. If you want to know what is happening inside your network, you will also need how the inner services are being mapped onto the outer services. So what is happening inside your VxLAN tunnel? So the easiest way to do is to say that your device has to support VxLAN extensions to SFlow. In that case, your SFlow will also visualize not only the outer tunnel, but all the services and all the applications which are going inside the tunnel. That's the easiest way to do it. To have VxLAN extensions to SFlow. However, there are multiple other things you need to consider. If you have an MPLS-based network, there is no current equivalent of traffic engineering inside a VxLAN tunnel. The standards, hopefully, will now come up which will mandate how to traffic engineer inside a VxLAN tunnel. There's also VxLAN for IPv6. Which is also being worked on. Another thing which is also needed is Y.1731. You can run Y.1731 performance monitoring, meaning latency, delay, jitter measurements across endpoints in an MPLS world or a G.8032 world. However, on a VxLAN, you'll need a Y.1731 support on a VTEP IP address. And there are many others, like PTP, time synchronization, and others. So essentially, if you are in a regional service provider network, this is a list of things which you might want to consider, whether you want to go with G.8032, whether you want to go with IP MPLS, or whether you want to go with VxLAN. The choice is entirely yours. So that's all I had on my presentation. Any questions? Nope. Thank you very much. Thank you.